Okay, let us start our class today. Let A be a square matrix, and suppose A has n linearly independent eigenvectors. Then we can, if we arrange all these eigenvectors, uh, let S equal to the eigenvector matrix. That is, it contains all the eigenvectors, let us say x1, x2, xn. So these are the eigenvectors, n eigenvectors we have. So we can write that A is equal to S D S inverse. And in some cases, in some books, you will find instead of D, you will find it as uh, sorry. In some cases, you will find it as S inverse AS equal to lambda. And either way, that is okay. Let us consider this lambda case today. By the way, regarding S, I have already told you that it's an eigenvector matrix. Regarding lambda, it's actually an eigenvalue matrix. Regarding lambda, this is capital lambda, uppercase lambda. Is eigenvalue matrix, which is primarily a diagonal matrix comprising all the lambda values, that is eigenvalues, and remaining values would be 0. So it's a diagonal matrix. With all eigenvalues along the principal diagonal. Okay, and remaining as 0. So this is how we can rewrite this. The matrix A times S, I can write it as matrix A times we have the eigenvectors x1, x2, xn. So we have the eigenvectors here. So it is something like we are multiplying the matrix A with the first eigenvector. The first row of matrix A with the first column, that is x1, second row with the first column, third row with the first column, and so on. And if you just see the other way around, this is actually um, A x1 equal to lambda 1 x1, right? Uh, A x2 is equal to lambda 2 x2, and so on. And remember, we initially told that we have independent, all the eigenvectors are linearly independent. So this is the scenario. So this can be written as A times x1. So matrix A times the first column, matrix A times the second column, matrix A times the third column. That gives you lambda 1 times x1, lambda 2 times x2, lambda n times xn. So lambda 1 times x1, lambda 2 times x2, and so on. Can this be rewritten as this last one, lambda 1 times x1, lambda 2 times x2, lambda n times xn? Can't we write it in this way so that what exactly is this? Uh, first row of first row is multiplied with lambda 1, right? There are so many elements here. So the first row, first row multiplied by first column gives you the first element here, second row times the first one, that gives you the second element here, and so forth. So this is what I can write it as. So that is what I have written. Like now you got why I call this one as an uppercase lambda. Uppercase lambda, this one is being called because this lambda matrix comprises only the lambda values, that is the eigenvalues. So this is what it can be written as AS equal to S lambda, which I can write it as so we have all these relations that will be using in our classes. Okay. So in all these cases, this is to be, this you can realize only when S is invertible. But then S is of course invertible because of its columns, because we have assumed the columns to be linearly independent, right? Say for example, I'll take a small matrix. So the first step is to compute the eigenvalues. Can you compute the eigenvalues? So to compute the eigenvalues, what we do, its determinant, we make it 0. So that becomes 5 into 2, 10, uh, minus 2 lambda, minus 5 lambda, minus 7 lambda. So how much the lambda would be?
8 and minus 1.
Yeah, that's it, I think. And of course, what is the eigenvector corresponding to lambda 1 that we found? How do we find a minus that ix bx equal to 0? That's how we do it. And of course, you will find the eigenvectors as 1, 2, I think. So uh, the first thing is the lum. Uh, First is the lambda matrix. The lambda matrix is it it doesn't matter whether you write -1 8 or 8 minus 1. It doesn't matter, but accordingly the S matrix, the eigenvector matrix has to be written. So the first one is 1, 2, 1 minus 1. And what is S inverse? Minus 1 minus 2, 1 upon minus 3. If I take minus common, this becomes the same matrix actually. So finally what I have is S1, 1, 2, minus 1, minus 1, 0, 0, 8. Does it equal to A? I guess it has to. Okay, so there are a few takeaways from here that has to be understood. Are if the eigenvalues of A are distinct, then eigenvectors are independent. And these two will lead to diagonalization. And these two will lead to diagonalization. All these things we are actually talking about the diagonalization, right? But then the the matrix S, the diagonalizing matrix S, is not unique. हेलो, नमस्कार। बिजी हैं थोड़ा। So the diagonalizing matrix S is not unique. You understand the very reason why it cannot be unique. Like you have S comprises the eigenvectors, and the vector multiplied with any constant would still be the same vector, and it would still be the same eigenvector, and therefore S cannot be a unique one. And of course, one more important thing. Not all matrices have n independent eigenvectors. Hence, not all matrices are diagonalizable. So, number of eigenvectors are responsible for the diagonalizability of the matrix, and of course, the invertibility of A depends on non-zero eigenvalues. Okay. Okay, we'll stop here today, and see you tomorrow in tomorrow's class. That's all for today.